Hello, ladies and gentlemen. Thank you and welcome once again to this another session of One Quantum Philippines presentation on quantum computing. One Quantum Philippines aims to make quantum computing accessible to Filipino people who are interested, and we aim as much as possible to introduce this uh, as early as possible to child's education. So, in our session today, we are very fortunate that one of our experts, the foremost expert here in One Quantum Philippines, is going to talk to us about dynamic quantum circuits. So, let me introduce him to you. So, his name is Brian Seigelwax. So Brian is an independent quantum algorithm designer, and he is an author of the two books, Dungeons and Qubits, an adventurous tale beyond the quantum computing tutorials, and Choose Your Own Quantum Algorithm, a personalized career guide for the quantum computing industry. So Brian uh, writes for Medium, Quantum Chais Zeitgeist, the Quantum Insider, Quantum Pirates, and QuantumGrad. So he will be talking to us about dynamic quantum circuits, giving examples, and talking about some of the advantages and disadvantages of using them. So, ladies and gentlemen, I'm proud to present to you Brian Seidelwitz. Take it away, Brian.
Thank you, Mr. President. Let's see if this works. Share screen. Let's try that, right? Do you see this? Can you see the slides? If anyone's talking, I can't hear you.
Brian, can you
Yes,
hear
can
me?
you see my slides? Can you see my screen?
Yeah, I can see your screen.
Okay, so if I change the slide, you can see that?
Yeah, it's now an agenda.
It should say agenda at the top?
Yes.
Okay. All right, we'll go with it then. All right, so we'll be talking about dynamic quantum circuits. My name is Brian Siegelwax, and the agenda for this talk is the announcements from IBM Quantum Summit 2022, the information that was given out at the IBM Practitioners Forum that was held the next day. I'll be going over examples of dynamic circuits, the advantages and disadvantages of dynamic circuits. I'll talk a little bit about a company called Quantum Machines, which may sound strange since this is mostly IBM, but we'll get there. And finally, I'll be happy to answer any questions anyone has at the end. IBM Quantum Summit 2022 is a sales and marketing event, so that's where IBM is basically making announcements of the latest and greatest. And one of the things that they announced is that dynamic circuits is now available on real hardware. It's actually been available since the very beginning on the simulator, but now more functionality is available, and it's available on 18 devices. And what dynamic circuits means is that we now have the opportunity to do real-time classical processing. What we do now is near-time classical processing. We do some classical stuff, we wait in a queue, we wait for the results, we do more classical stuff, we wait in a queue, we wait for the results, and that waiting part is very slow. What dynamic circuits does is we're taking that classical mid-processing in particular, and we're putting it right next to the quantum processor. So we go to the quantum computer one time, we do everything we have to do, we get the results, we do our classical post processing, and we're done. One trip to the quantum processor. One of the things that dynamic circuits allow is the opportunity to remove gates from our circuits. Every single gate introduces errors, so the more we can take out, the less overall errors we'll have. Dynamic circuits also allow feed-forward operations, which is the image on the right here. We have the U1 block, which can be any number of operations. We then perform some measurements, and based on those measurements, we are dynamically extending the circuit with the U2 block and whatever operations are in there. And we can continue with additional measurements and dynamically extend the circuit with the U3 block and whatever operations are in there. Dynamic circuits also give us the opportunity to trade depth for width. Generally speaking, the deeper the circuit, the noisier it is. So if we have more qubits available, generally speaking, we can make a wider circuit, a more shallow circuit that has less errors, and dynamic circuits just give us more opportunities to do that. This image is from this website here, where you can also get all of the announcements that were made during IBM Quantum Summit 2022. And I mentioned that dynamic circuits are now possible on 18 backends, and most of us are going to care about these 3 open backends because that means they're free. And if you go into the IBM Quantum portal and you look at the list of backends that you have available to you, you'll see that these 3 are marked OpenQASM 3, and that's the indicator that dynamic circuits are possible. So we have the 5-qubit IBM Q Manila and 2 7-qubit devices, Oslo and Nairobi. The more gates we can remove, the less overall risk of errors we have. This here is a 2-function Deutsch-Jozsa algorithm, which has no practical usage, but what we want to focus on for this talk is the X gate at the very end of the middle qubit. That X gate introduces a small additional chance for errors, but it's completely unnecessary because whether this is the end of our circuit or the middle of the circuit, we can do that classically. We can place a measurement right there, and whatever the result of that measurement is, we can mimic the effect of the X gate. If we measure to 0, we can classically flip that to 1. If we measure a 1, we can classically flip that to 0. That X gate is unnecessary, but one single qubit operation is not impressive. So let's take a look at this one here, which is just a Qiskit demonstration of visualization. So it's not meant to do anything in particular, but to show off what Qiskit can visualize, how Qiskit can visualize circuits in particular. And what I'd like to focus on are the purple controlled swap gates, also called Fredkin gates, and what looks like one operation in practice is a minimum of a dozen time steps. So it's multiple single qubit and multi-qubit operations, but the circuit depth that it adds is a minimum of 12. So it's much deeper than even the circuit we're looking at on the left. And we have 3 of those. So we're talking about a considerably deep circuit now. And every operation, every single qubit operation introduces errors. Every multi-qubit operation introduces even more errors. But we can completely remove these 3 controlled swaps from the circuit, and we can place the measurements right after the Hadamard gates. And then what we can do classically is we can look at QB0, because that's the first control. And if we measured a 1 off of QB0, we can classically swap the measurements that we took off QB1 and QB2. We can then look at the measurement from QB2, and if that's now a 1, we can classically swap the measurements that we took off QB3 and QB4. And then we can look at the state, the bit now from QB3, and if that's a 1, we can classically swap the measurements from QB4 and QB0. We can remove those three controlled swaps. We can reduce all that circuit depth. We can prevent all the errors that those three gates would have introduced. And while we're at it, we might as well remove the X gates in the beginning as well. If we look at QB3, and that's initialized in a state of 0, when we apply a Hadamard gate, we're moving to the plus state. The plus state is an equal superposition, which just means that we have an equal probability of measuring 0 or 1. Now, if we look at QB4 with the X gate, we're in the 1 state. When we apply a Hadamard, we're going to the minus state. And for those who aren't following along with that, we're just in an equal superposition again. We have an equal probability of measuring 0 and 1 again. So for this circuit, between having the X gate and not having the X gate, it makes no difference. We have an equal probability on all of these qubits of measuring a 0 or a 1. So we're left with just Hadamards, just measurements, and then some classical swaps afterward. And ideally, what we would want is some kind of amalgamation or mashup of these two circuits where we have a legitimate quantum circuit like the one on the left, and we have something a little more error producing than a single X gate, perhaps a Fredkin gate, the controlled swap. Now, if we can imagine the circuit on the left with a controlled swap where the X is, now we have a lot more circuit depth, a lot more chances for errors. And again, we can remove that, we can measure early, and we can classically swap the bits if we measure a 1 on the control qubit. We have more opportunities to trade depth for width. So this is unfortunately a random circuit. I'm not a big fan of using these, but this is IBM's example, and I have not had a chance to experiment exclusively with this. But the circuit that we're looking at here has some pretty good depth just by looking at it, but it's actually deeper than it would appear because we have 4 swap gates. And each of those swap gates has a minimum of 3 multi-qubit operations, and that's if the qubits are directly connected. If they're not directly connected, it's actually a much more deeper circuit than that. And what we can do with this is if we have the qubits available, each of those 4 qubits can be paired up with an ancilla qubit. We can perform some mid-circuit measurements, and we can classically perform bit flips and phase flips and generate the same random outcome as we would with the circuit on the left, or for that matter, any other random outcome with the circuit on the right, which is far more versatile. And applications identified for dynamic circuits include quantum error correction. Syndrome bits are the same classical bits that you're used to using, except that they have a different name because we're using syndrome bits to do stuff within the circuit. In the case for error correction, we are detecting and correcting bit flip and phase flip errors. Also, quantum simulation, and I will be showing an example of a dynamic variational quantum eigensolver in a little while. And quantum machine learning, I'll also be showing an example of clustering and classification. The IBM Quantum Practitioners Forum was held the next day, and one of the things that they announced there was the staged pass manager. So what you do is you design your circuit, and before you execute it, you transpile it and optimize the circuit before it runs. Qubit selection and removing operations that are not necessary. For example, you have 2 X gates in a row, they cancel each other out. You don't need them to be in there. But what they announced was a staged pass manager. The process of transpiling and optimizing the circuit can be done in stages so that you have more control over it. But more importantly for this discussion are the custom presets for error suppression. So imagine we have 2 qubits and one is being acted on dynamically. We initialize it, we use it, we measure, we reset, we reuse, we measure, we reset, we reuse. And the other qubit is just, oh, maybe it's doing stuff, but it's not being measured or reset. It has to maintain its coherence for the entire length of time that this other qubit is doing all this other stuff. So the pass manager now has custom presets for dynamic circuits to help with suppressing errors for those qubits that are not being acted on dynamically. They also announced delay operations, which actually have been around for a while, so I don't know why they were re-announced. But anyway, in the beginning, we go back a few years and you designed a quantum circuit. You initialized your qubits in the beginning and you measured them at the very end. Then a couple of years ago, IBM announced mid-circuit measurements. And now we can measure anywhere in the circuit. But also what it would do is if you have a qubit and you're done with it, it used to have to wait until all the other qubits were finished before you could measure it. But if your qubit is finished, it can go ahead and be measured right away. It doesn't have to wait for the others. The measurement gets moved forward. And what we can do on the other end with delay operations is imagine we initialize a qubit, but we don't need it right away. It still has to maintain its coherence until we need it. Or what we can do is we can delay when that qubit starts to be used. And what we're doing is we're moving closer together the time that we start using the qubit and the time that we measure the qubit so that the quantum state has to be maintained for the shortest amount of time. Then Mathematic can, in principle, be applied manually. It is a utility that is now built into optimization level 3, which is the pass manager preset that you should normally use, the highest setting. And optimization level 3 does not yet work on dynamic circuits. You can use optimization level 0 and optimization level 1, and depending on who you ask, optimization level 2. But Mathematic, which I will talk about a little bit on the next slide, can be applied in principle to dynamic circuits. Also, in principle, any conditional operation should work. That's actually not true because I've found one that does not work. But in principle, anything you would want to do to construct your quantum circuits now can be used conditionally, which means that you take mid-circuit measurements, and depending what the measurements are, the operation should happen. So in principle, every operation should work, except for one. Then that includes nested conditional statements, which means that we have mid-circuit measurements and we have conditional statements. And if that condition is met, we can go ahead and apply another round of conditional statement. So two conditions have to be met in order for the operation to actually execute. This is all brand new stuff. It was just announced last month, but because this is all new stuff, you need the latest versions of Qiskit. And also, there are more OpenQASM 3 features than are presently available in Qiskit. So if you're looking at the OpenQASM 3 language specification and you're trying to use a feature that's not working, there is a possibility that Qiskit just hasn't implemented it yet. And if you do a search online, if you just put Qiskit and OpenQASM 3, it should bring you to the list of OpenQASM 3 features in Qiskit, which ones have been fully implemented, which ones have been partially implemented, and which ones have not been implemented yet, with the goal that eventually all of them will be implemented. But right now, there's a subset available. Also, the control systems have memory limits. The hardware that controls the quantum computer, the more mid-circuit measurements that you want to do, the more conditional operations you want to do, there are limits to the hardware, and they are not clearly defined how much we can do dynamically just yet. I know I've broken well past the limits, and I'll discuss that a little bit later. but we can use dynamic circuits now. But if you push it a little too much, the control systems can't quite handle it yet. But control systems are classical, so that's just a matter of time, I believe, in IBM. So I mentioned Mathematic, which is a great library if you don't already use it. And I'm going to talk about IBM Q Manila. Why? Because this is one quantum Philippines. Why not? And the qubits on IBM Q Manila, there are 5 qubits. And if we look toward the bottom of the screen, we can see that they're not necessarily in a straight line like that. But this is showing how the qubits are connected. The lines connecting the qubits show how they are connected to each other. And now imagine we have a circuit where we want to entangle qubit 0 and qubit 4. We can't do that because qubit 0 and qubit 4 are not connected. And one of the things that IBM has always done, which not every provider does, in some cases you're responsible for this yourself, but IBM has always, when it transpiles the circuit, automatically added the necessary swap operations to make it possible. So let's say, for example, we swap qubit 4 with qubit 3, then we swap qubit 3 with qubit 2, then we swap qubit 2 with qubit 1, and now we can entangle qubit 0 and qubit 1. But all those swap operations add a ton of depth. They're time consuming. They introduce a ton of errors. So we're going to get some pretty messy results here. And what Mathematic does is says, it looks at your circuit and says, you have selected qubit 0 and qubit 4, but what we're going to do is we're going to map those qubits, let's say, to the physical qubit 0 and 1. So what you see in your notebook on your circuit diagram as 0 and 4 is physically 0 and 1, and then 0 and 1 get entangled. You can measure it, you get the results back. All those errors are prevented by using Mathematic and having better qubit selection. So that's what, and then when the results come back, you still see it as your qubit 0 and qubit 4, so you're not confused, but physically you used qubit 0 and 1, or whatever the best qubits happen to be at that time. This is the old way of doing dynamic circuits. This is something I did years ago, and it's always been available on the simulator, but could not run on real hardware. And if you can imagine a block sphere, and we have 2 quantum states near each other on one side, and we have 2 quantum states near each other on the other side. So we have 2 obvious clusters. And why is that number so small? Because of limited qubits. But what we're doing is we're introducing another quantum state, and we want to classify that state as being either closer to one cluster or to the other clusters. So the left side of this circuit is the clustering, and the right side of this circuit is classification. And for those who are unfamiliar with what we're looking at, I'll quickly walk through from left to right, starting with the orange rectangle. You're familiar with Python functions. OpenChasm 2 has subroutines, and back when I created this circuit, this is how those subroutines would appear on a circuit, and they could consist of any number of operations. But however many operations there are, they would just appear as this maroon rectangle on the circuit diagram. The next to that, we have in red a reset gate. Resets have always been available on the simulator, and within the past couple of years, they became available on real hardware. And what we're doing in this case is we're reusing qubits to reduce the total number of qubits that we need to simulate. So the simulator works the exact opposite of real hardware in the sense that the more qubits you simulate, the slower it gets. So if I try to simulate 10 qubits on my laptop, I can go get a snack, I can freshen my coffee or whatever. And at 20 qubits, even using IBM's simulator, you can reach the runtime error which is 10,000 seconds, which I learned the hard way. So for the simulator, you want to use as few qubits as possible. You want a narrow circuit, and you can go as deep as you want. The simulator doesn't care. I've done some mightily deep circuits, and it's fine. But now on real hardware, it's the exact opposite. If you had a circuit even this deep, you're just going to get pure noise. So you want to use more qubits and less depth on real hardware, polar opposites. But here, what we're doing in red is we're reusing qubits so that the simulation is faster. Next to that in yellow is a barrier operation, which I have historically used for presentation purposes to keep all the operations separate for explanations. Normally, you would want to remove these from your circuit before running it. But one of the things barriers have always done, even before the delay operation, and I mentioned the delay operation earlier, the barrier also functions in that capacity that if you have qubits that are not being acted upon, you can push backward with previously with barrier operations. Now there's a specific delay operation, and you can push back those operations. So again, they're closer to the measurements, and the state has to be maintained for less time. Then in green, we are taking the mid-circuit measurements. And then in light blue and blue, this is where the dynamic stuff is really happening. In light blue, that's where we're testing the conditions that for the bit that we're looking at in light blue there, if the bit is a certain value, then we execute the operation in blue above it. So on the circuit diagram, we're seeing all these operations, but all, some, or none of them might actually execute. It all depends on meeting the conditions of what's in light blue. And then at the very end in purple are the final measurements that help us determine our new quantum state, whether it should be classified as one cluster or the other. And this is the new way of doing it with some sample code on the left and the circuit on the right. So we'll start with yellow. That's a Hadamard gate, which, like the controlled swap, does not actually exist. There's no such thing as a Hadamard gate, but it exists for ease of use because it's used so frequently. But a Hadamard gate is really what you see on the right-hand side, three basis gates. IBM quantum computers have five basis gates, only five operations that they actually recognize. And those operations are then compiled into microwave pulses, which actually affect the hardware. So the Hadamard gate is broken down to the operations in yellow. And then we perform a mid-circuit measurement to the syndrome bit. Then in green, what we're doing is we're testing the syndrome bit. If it measured a 1, we will apply an X gate to qubit 1, and then we'll take the final measurement. So what we will end up with is either 0, 0 or 1, 1, which is normally the sign of entanglement, but in this case, there is no entanglement going on. We're just kind of faking it. But the important part of this slide is what you see in yellow could be any number of operations on any number of qubits. What you see in green can be any number of operations on any number of qubits. And we don't have to stop here. We can keep going, as we can see with the variational quantum eigensolver, which is used for quantum chemistry. And we'll start with the efficient SU2 block, and that is the Onsat. So if you've ever heard that name before, it's just a circuit with some random parameters. And you'll never see VQE this short, but anyway, we'll take some measurements, and based on those measurements, we will update the parameters and redo the circuit. Then we'll measure again, we'll update the parameters, we'll recreate the circuit, and we'll keep on going until we've optimized the parameters. If you try to do this from your laptop, it is really, really slow because the The updating of parameters takes place on your laptop, computer, whatever you have. So you design the first circuit, you wait in a queue, you wait for the results to come back, you update the parameters locally, you wait in a queue again, you wait for the results to come back, and that's a very long time. And this is one of the reasons why there is Qiskit runtime. Qiskit runtime is a service that puts your code closer to the quantum computer so that your wait for the quantum computer is shorter and so that the classical code executes faster. Or you can also reserve a quantum computer if you're in an organization that can do that. But that still takes time, even with Qiskit runtime. It still takes time to go to the quantum computer, wait for the result to come back, go to the quantum computer, wait for the result to come back. So imagine we could do that dynamically. We go to the quantum computer just one time, get the results back, do our classical post processing, and we're done. If you've ever run VQE before, that is a huge time savings. And I also want to point out before I proceed that you'll probably never design the circuit quite like this, where we have the syndrome classical register, and then at the bottom, the measure classical register. This you need classical registers for the measurements that you want to retain. So if you don't care about the mid-circuit measurements, you could actually have just one classical register. Then all you get is the final measurements, you do your classical post-processing, and you're done. If you do care about the mid-circuit measurements, each set of measurements needs its own classical register, but then you'll be able to retrieve all of those results. But you'll probably not see a hybrid like this where there are three measurements and two registers, but there are space constraints. My focus has been on Qsync too. Qsync is a generative algorithm to compose music, and like VQE, the first version was very slow. We have to generate the next note to know what to send to the quantum computer to generate the next note. So we generate a note, we wait on the quantum computer, we generate the next note, we wait on the quantum computer, we generate the next note, we wait on the quantum computer. So it could take hours to compose a relatively short tune, depending on queue times. But now imagine you can wait in a queue just one time and compose an entirely new song. You send it once, a long bit string comes back, you classically post process it, and you have new music just like that. In principle, it works. It works on the simulator. You can compose a new tune, and this isn't a small scale thing, but takes a few minutes to run, which is actually a lot better than I thought it would be to do classically on the simulator locally. But the hardware needs some catching up to do to actually do this on real hardware. When I mentioned before that we could do every conditional operation in principle, one of the things we cannot do is a conditional initialize statement. And the initialize function is the easiest way to encode amplitudes onto qubits, and that's how Qsync works. So without being able to use that function, it would be an absolute nightmare to manually do amplitude encoding, which also runs into a second problem, the number of conditional statements required. So to compose a song, we need to perform hundreds of measurements, and each mid-circuit measurement needs hundreds of conditional statements. So the hardware just can't keep up with that. But the reason why that wouldn't work is that a dynamic circuit, or any circuit, has to execute within the coherence time of the qubits. If you've run any quantum circuits at all from the very beginning, when you do something small, you know that there's noise in your measurement results. And as your circuit gets deeper and deeper, you can see it get noisier and noisier and noisier. And a fun thing to do, unless it's important for work, but a fun thing to do is to keep adding depth until you get a uniform distribution where the circuit is so noisy, all of the possible outcomes are roughly the same, and you can't get any information out of it at all. And what you can do from there is you can keep adding even more to it. And eventually, what will happen is the qubits will relax and all go to zero. So, yes, I have done that before. But the problem with, or the challenge with dynamic circuits is that you only have a limited amount of time, and we're talking milliseconds here, that every quantum operation takes time. The slowest thing that we can do is the measurements, actually, and possibly second to that. I don't have it fully broken down how long everything takes, but close to that would be all the conditional statements and all of the classical things that we can do now. So if you have something grandiose like this, you're having delusions of grandeur and you want hundreds of measurements and hundreds of conditional statements, the qubits will probably all measure zero at the end of it'll probably just be a ton of zeros. But because the initialize statement, the conditional initialize doesn't work, that's a problem before even getting to all of that. The amount of classical required. So some of the new circuit design features in dynamic circuits include variables. OpenQASM2 has had variables in the form of the parameters for subroutines, but now there are real variables, and these differ from the variables you normally use. We're not talking about Jupyter notebooks or Python variables. The Python variables stay local to you. They're on your laptop or whatever you're using. And we're talking about variables that have information next to the quantum processor. So in the case of a dynamic VQE and we're updating parameters, those variables are not local, that we're using memory in the control systems. We can also do if-else statements. Everything I've shown you so far has been if-then statements, but if-else statements are now possible. And also loops, which don't look like any, well, I was going to say they don't look like any loops I've seen before, but they look like, well, I'm not going to say what it looks like because it'll scare people, but it's awesome. But anyway, we could do kind of mimic loops for a while using whole register operations, which means you apply some operation to entire quantum register at one time. And if you were to do that classically, you would do that in a loop. So that's how close we've been able to do with OpenQASM2, but now there is a lot more loop functionality. And it's easy, by the way. I don't want to scare anybody with that, but we have loop functionality now and classical computation. So in the case of dynamic VQE, we've got these parameters. We need to be able to update them next to the quantum circuit in order to make them useful. So classical computation is available next to the quantum processor. Then you can also make measurements conditional. The circuit we looked at before, circuits we looked at before, the mid-circuit measurements, the final measurements, and we can decide what we want to keep with the use of classical registers. But the mid-circuit measurements, if a condition is met, you can take an additional set of measurements. The main difference being that if the measurement is being executed conditionally, the measurement results are not retrievable at all. Those are lost. It'll still work, your circuit will still function, but the information as to what was actually measured is not retrievable. And there are features like modifiers and timing, which I haven't had a chance to get into, but the point being is you have a pretty well-developed language now. OpenQASM2, which is my favorite language, has fairly limited features. It's a very small language. And now there is a lot more added to it. It's still not as complete as, let's say, languages where you'll notice there are no data structures here. And you can fake data structures, which is beyond the scope of this presentation, but you don't have lists and dictionaries and things like that. So those have to be faked with conditional logic. And then we have the problem that I mentioned before where conditional logic takes time. But you still have a lot of added functionality here. And if you have any questions, there is a Qiskit Slack channel dedicated to dynamic circuits, and it is called Dynamic Circuits. And also, a fun thing to try is ChatGPT, which is in the news. Everybody's talking about it. And it really knows what it's doing. Not that it's going to design the whole circuit for you, but let's say you have a question: how can I implement OpenChasm3 variables in Qiskit? I actually haven't seen that published anywhere, but if you ask ChatGPT, it actually knows. If you ask it how to implement loops, OpenChasm3 loops in Qiskit, because you have to make that distinction, not Qiskit loops, but OpenChasm3 loops, ChatGPT has that information already somehow. So it can be very useful for code questions. It's got little samples, and everything I've looked at is good. So there are new things that IBM announced that are not directly related to dynamic circuits, but can be used in conjunction with dynamic circuits, including circuit cutting. So let's think about dynamic VQE, and we want to simulate a water molecule. And we just have free accounts, so we have access to 5 qubits and 7 qubits, and a water molecule needs 10. That's a problem, except that if you have a circuit, if there's a point of weak entanglement, you can cut the circuit at that point and then classically knit the results together to simulate having a larger quantum computer, in this case, the 10 qubits that we need. Another thing that can be done with circuit knitting is imagine you want to do multiple experiments at the same time. We want to model a lithium hydride molecule with 3 different geometries, and that's beyond the scope of this presentation as well. But we have Manila, Oslo, and Nairobi devices available. We can simulate the 3 different geometries on 3 different quantum computers at the same time and classically knit the results back together and do our classical post-processing. And a good example of this, and I'll keep using dynamic VQ as an example, that entanglement forging is a good example. This is something IBM came up with a specific mention of the water molecule because it needs 10 qubits, and 5 of those qubits are for spin up and 5 of those qubits are for spin down. And they determined, well, that's a good place to cut the circuit. So you cut the circuit right there, and you send the 2 halves to 2 different quantum computers, and then classically knit that back together. And now you can simulate a water molecule without having a 10 qubit or larger quantum device. Quantum serverless, I compare to Gmail, which is what I use. I have no idea where in the world my email servers are, and quite frankly, I don't care. And that's where IBM is going with quantum computers, that you should be able to focus on your quantum circuits, you should be able to focus on your algorithms as if you're working with the simulator. You don't care how many qubits you have, you don't care how they're connected, you just design it to do what you need it to do, and then quantum serverless will handle that for you. Which quantum computer or quantum computers should it run on? That'll be done seamlessly in the background. And then as an extension of that, IBM Quantum is just a division of IBM Research, and IBM Research does a lot more than quantum. So the idea is that you're not going to be developing quantum algorithms in a vacuum, you're going to be developing applications. And those applications could need a variety of resources. So let's imagine we want to develop some software to simulate molecules for material science. And middleware looks at it and says, you know what, we have a multi-core CPU. We can do quite a bit locally. We don't need anything fancy for that. But when it comes time to simulating the molecules, That gets sent off to quantum serverless, and the quantum algorithms get executed, and the results come back. And now let's imagine we want to do some fancy visualizations, and the middleware determines, GPUs would be pretty handy for that. So maybe let's send that off to IBM Watson. Maybe not the best example, but the point is all of the different resources that you might need, the middleware will seamlessly handle. The quantum stuff goes to quantum serverless, which seamlessly handles which quantum computer or computers we're using. But IBM has a whole lot of other stuff, and all of that will be built into that, handling the resources so you can focus on the functionality. So to review the advantages and disadvantages of dynamic circuits, the advantages include the opportunity to remove gates from our circuits, which reduces noise, the opportunity to trade depth for width, or more opportunities to trade depth for width, which also reduces errors, and most importantly, it's faster even than Qiskit runtime. Just one trip to the quantum computer and we're done. Some of the disadvantages include too much classical logic. I see there being an opportunity for something that is quantumly hard to do. There might be the opportunity to do it classically, and now that kind of defeats the purpose of using a quantum computer. You want to compute quantumly for computational advantage. And despite the talk of being able to remove an X gate and do that classically, or removing a controlled swap and doing that classically, there's the danger, I think, of doing maybe too much classically, and then you've defeated the purpose of using a quantum computer. There are also control system limits, so you can start experimenting with dynamic circuits now. But if you try to do too many mid-circuit measurements or too many controlled operations, you could hit these limits. Then coherence limits, the example I gave earlier of the 2-qubit circuit where one qubit is being acted upon dynamically and the other one isn't. One of the things that you want to watch out for in your circuits are the qubits that are not being acted upon dynamically. They're not being measured, they're not being reset. They need to maintain their coherence for a relatively long period of time. You want to watch out for that in your circuits. Also, the other qubit is not free from danger either. In principle, we initialize a qubit, we use it. We measure, we reset, we reuse. In principle, it's that point there. The qubit now has to maintain its coherence until the next time it is measured, in principle. In practice, it's not quite that perfect. We look at that qubit, we initialize it, we use it, we measure, reset, reuse, we measure, we reset, we reuse, and that process is not free from errors. It's not a perfect process either. So even the process of reusing a qubit has the potential for errors as well. And we cannot use OpenQASM 3 in the circuit composer just yet. It's still OpenQASM 2. And it'll be better, in my opinion, to use the composer because I'm biased. I love using the composer. But you can imagine a situation where you declare a variable and it's in Python. And the problem with that is, depending on the algorithm, that variable is local to your computer. And what we're talking about in dynamic circuits is the variable that's next to the quantum processor. And if we're working in the composer, all we're working on is what's happening on the circuit, what's being done during runtime, what conditional logic is being applied during runtime, and you can focus on that aspect, and it reduces the danger of perhaps you're using a classical loop in Python in your Jupyter notebook, but that's not affecting how the circuit is actually being extended during runtime. So similar concepts, but where's the action happening? The composer would allow some focus, and plus, it's just awesome to use. And Quantum Machines, if you're not familiar with the company, that's the name of a company based in Israel. And the articles that I've been writing on dynamic quantum circuits caught their attention. And I'm going to start with a disclaimer that so far I've only seen a presentation. I have not been hands on, but I hopefully will have direct access soon, and then I will write about it and update these slides. But what they have is dynamic pulse control. So, what we've been looking at are circuits and gates. And I mentioned in the case of the controlled swap and the Hadamard that these gates are transpiled, they are decomposed into these basis gates, and then those basis gates are compiled into microwave pulses. And quantum machines operates at that lower level. They have dynamic circuits similar in execution to what we're talking about here, but at the pulse level. So if you've used Qiskit Pulse, this might be of interest to you. Now, OpenQASM 3 does support this. OpenQASM 3 has dynamic circuits and pulse control. So in principle, dynamic pulse control is possible, but from asking around, it has not been tested yet. So even if it is possible, Quantum Machines is further along in that regard. And also by virtue of having done dynamic circuits longer, it appears, and again, presentation only, it appears again as though more real-time classical processing might be possible with quantum machines. So we reviewed the list before. OpenQASM 3 has variables and conditional statements and loops. Excuse me. It looks like there might be more possible with quantum machines. And what can we fully do with quantum machines? That is a great question. And speaking of great questions, I will be happy now to take yours. How about that for a segue? How do I exit out of here?
Hi, Brian. Thank you very much. Are you able to hear me?
Yes.
Okay, so we have a first question here from Asher. So the question is IBM dynamic quantum circuit available to all who have IBM Q Experience account, or is it a paid feature?
That is a great question. It is absolutely free. And that's why I singled out Manila, Oslo, and Nairobi devices because they're also free access. So dynamic circuits are part of Qiskit, well, partially implemented in Qiskit, and OpenQASM 3 is open source also. So yes, with a free account, a completely free account, you can use dynamic circuits right now with those three devices. And if you have access to the researcher program or anything like that, then there are 15 more devices that are paid for.
Thanks for that, Brian. Uh, so there's another question here. It's actually from me. I'm just going to merge the two questions. So I saw that. So you discuss about the new features and do you have any examples how to use them? Like, for example, the while or the for loop, and if else. Are these new features? Um, uh, can we already use this in Qiskit? Like, how do you invoke them?
Yeah, if else I haven't gotten into yet, but it might be probably could. I could probably modify the clustering and classification algorithm to do if else.
Mhm.
And it works differently from how it used to work. Also, it used to be an if statement for each conditional operation. So if this bit equals 1, do this. And if you want to do multiple operations, you need if statement, if statement, if statement. And now you can just do if and have a series of things. So I haven't had to use else yet, but if you have a multi-bit register, then that would be the need for that. So the example I showed were was a single qubit register, but a single bit register. But then the dynamic VQE one, where it showed 3-bit registers, a 3-bit syndrome bit, and a 3-bit final measurement. But the 3-bit syndrome bit, that would be a possible use of it if else. So 3 bits. So at decimally, if that's a word, the value of the register will be 0 through 7 because it's 3 bits. So 2 to the 3, 0 through 7. So what we can do there is if the syndrome classical register, the other question that was on screen, ancilla are qubits and syndrome is bits. So
Oh,
quantum versus classical. So if the syndrome register equals 0, then do this. Else, if the register equals 1, do this. Else, if it's equal 2, then this, or 3, then this. So that would be the case up for if else when we have a 3-bit register like that and 8 different options of what might happen. Then for loops, the most interesting thing I've seen for that would be for error correction. That while a qubit exists in a certain state, you can keep testing to see if you need to correct a bit flip or phase flip error, which is really interesting. I haven't done that myself yet, but while we're doing something with this qubit, let us detect and correct errors. So that looks like the most interesting application for that.
thank you, Brian. So here's another question from Asher. How do dynamic quantum circuits compare to static quantum circuits in terms of their ability to mitigate errors?
Well, the word mitigate would be there's so many terms for errors, error correction, error suppression, error mitigation. Error mitigation would be after we're done executing technically. So, but generally speaking, a dynamic circuit is, or a static circuit, we design it, we run it, and mitigating errors is a complicated process of determining how the errors are happening and then correcting for them afterwards. But dynamic circuits, the error correction we could do is during runtime. So with a static circuit, the errors are happening and there's nothing we can do about it. We measure, we mitigate afterwards. And with a dynamic circuit, we can try to suppress and correct errors during runtime and then also mitigate them after we're done. So it's the potential to reduce errors by a lot more.
Thank you for that, Brian. So we have another question from Burns. Is there some schematic editor to be able to wire these circuits? I think he was talking about the part where you were talking about uh, using two different quantum computers with different capacities, like 7 qubit and 5 qubit, and then uh, running these two algorithms and then piecing them together at the end. So the question is there a schematic editor to be able to wire these circuits
Yeah,
together?
I can imagine two different things. So for circuit cutting and circuit knitting, they didn't actually show. I'm trying to remember. I don't think they showed an actual example of that. There's a paper maybe that was written for entanglement forging. So that would be the search. Entanglement forging would be the experimental using a molecule of water, cutting and knitting the results back together. But I don't think there's any kind of graphical interface for that. And then for a single circuit, anyway, that would be the use of the IBM Composer, which is not yet ready for, or it's not yet compatible with OpenChasm 3. But in general, actually, I use the Composer for OpenChasm 2. But there is a drag and drop circuit builder, which is not heavily advertised. But you've got the Asher's last talk where he was showing how to use the IBM quantum experience, and he was showing the circuit diagram, and you can change how many qubits you have, and you can drag and drop things on there. So you can actually build a quantum circuit quite easily. But now that's still OpenChasm 2, and hopefully at some point that will be OpenChasm 3, so that all of these new features can be implemented. And then if we're talking about cutting and knitting, I honestly have no idea how to actually implement that. There might be some insights into the entanglement forging paper, but yeah, that's pretty advanced stuff. So I don't know is the answer for the second part of it.
Yeah, no worries. So yeah, question from me. So how do I use a dynamic circuit, or is there like a keyword that will tell us that this part is already a dynamic circuit, or is it all transparent to the user?
Well, if you have the latest version of Qiskit, you can just start using the features. And if you try to run them on a non compatible backend, for example, IBM Cube Bellum is a 5 qubit device that is not OpenChasm 3 compatible yet, so it's just not going to work. But if you select as your backend either Manila, Oslo, or Nairobi, or any of the other 15 devices, if you have access to them, you can just start using it, and it just works. Just like what you've been doing, it just works. And the difference being that if the device is not OpenChasm 3 compatible, it's just not going to work.
Okay, so we have a last question here from Burns. Uh, can a quantum circuit be wired to create a closed loop feedback?
Um, well, you can't go backwards. It's like playing a song where you start at the beginning and the musical sheet is the quantum circuit and it just plays as it goes along. But you could you can recreate the circuit. So I don't have a circuit and then I go back and loop and update parameters and rerun it, but I can just create it again with the new parameters like the dynamic VQE example. I'm not updating the same circuit. I am Well, the way we do it now, so we have the circuit and we send that, and then what we are doing is we're recreating it with updated parameters and we're sending it back down, and we're essentially doing that same thing, recreating the same circuit with the updated parameters, except that if you looked at the entire dynamic circuit, it would be one long, super long circuit by the time it's done, but you can't actually go backwards. You can just kind of fake it by recreating it as you go forward.
Okay, so that's actually the last question. Yes, so Do you have anything, any last things to say, um, Brian?
No, I hope everyone found that informative. I hope I didn't speak too quickly in any parts. And thank you for letting me present dynamic circuits.
Yeah, thank you very much. Okay, so I guess that's it. Thank you very much. Yeah, so dear friends, for joining us in this very interesting presentation by Brian. So I hope that you'll join us in our next session, and it will be um, next year. And if you're interested, we would like to invite you to our Facebook group, One Quantum Philippines. And uh, yeah, uh, we hope to see you there, and we hope that you'll help us to make quantum computing, uh, make Filipinos more aware of quantum computing. So thank you very much, and see you in our next session. Bye.